Hey you guys, this is Mr. Millings, and in this video we are going to learn about Le Chatelier's principle and the Haber process, and we are going to apply Le Chatelier's principle to the Haber process. So let's start talking about the Haber process and see what's going on. So let's give you some backdropping as to what was going on back in the late part of the 1800s and early part of the 1900s. It says right here, without some sort of reaction or process that would add more nitrogen into the ground, thus aiding in higher crop yields, farmers would only be able to produce enough food for about 4 billion people. The problem is that today there are about 7 billion people on our planet. So without this gentleman's discovery, Fritz Haber and the Haber process, there would only be enough food on our planet for about 4 billion people. So who is Fritz Haber, and what were his contributions to chemistry and to our world for that matter? Well, it says right here that Fritz Haber was a German scientist that lived between 1868 and 1934, and he ends up winning a Nobel Prize in chemistry in 1918 for his huge contribution to our planet and to chemistry, this process right here called the Haber process. And so here's how it works. In order for plants to produce crops that we can later eat, those plants need nutrients themselves. They need food themselves to grow in order to grow. And what food do they need? Well, they're going to need some nitrogen. They're going to need nitrogen, right? We know that 78% of Earth's atmosphere is nitrogen gas. So you might be thinking, well, plants have plenty of nitrogen gas, they have plenty of oxygen, they have plenty of water, they have plenty of sunlight, so no problem. Well, the issue is that nitrogen gas that is found in the atmosphere has a triple bond between it. It looks like this. These nitrogen are held into place by a triple bond. And so in order to break this triple bond here and use the nitrogen as food in the form of nitrate, the plant is going to have to utilize a tremendous amount of energy to break this chemical bond here, and they just can't do that. So what ends up happening is that the nitrogen gas that is in the air, these plants just can't use. However, if it's in the dirt, right, if it's in the dirt, if this nitrogen is in the dirt in the form of nitrate, well then those plants can use this nitrogen here to aid in their growth and eventually to produce crops that we can then eat. So what the issue is that Haber discovered or found was that we had to increase the amount of nitrogen that is in the soil in order for those plants to grow and produce crops that we can then eat. And so when he comes up with this Haber process right here, essentially what he ends up doing is he takes nitrogen gas from the atmosphere, reacting with hydrogen gas, and ends up producing ammonia, NH3. And this ammonia is then put into the ground, where those plants can then convert it into nitrate and use the nitrogen as food or some nutrients in order for them to grow and produce crops that we can then eat. All right, so the more ammonia that we can spread around into the soil and on the topsoil, well then that means more food for these plants, right? And that means more food for us. And so this Haber process here is a very important process because it basically revolutionizes farming in our country and throughout the world, and allows us to produce higher yields of crops that we can then eat and feed the 7 billion people that are on this planet. All right, so it says right here that ammonia is one of the most widely produced chemicals in the world, and 80% of it is used in fertilizer to aid in higher crop yields. It is injected into the ground, and plants use the nitrogen from it and combine it with oxygen to form nitrate that plants use as food. So because of this process right here, taking nitrogen gas from the atmosphere and reacting with hydrogen to produce ammonia that plants can then use the nitrogen from as their food source, we are now able to feed as many people as we need, right? The 7 billion people on this planet can now eat because of this process right here. However, there becomes an issue here. How can we increase the production of NH3, of ammonia? How can we increase the production? How can we perform this chemical reaction more efficiently? Well, If we take the Haber process and we apply the ideas of a gentleman by the name of Chatelier, then we can increase the production of NH3 and make this chemical reaction here a lot more efficient. So let's take a look at that. Let's go ahead and apply Le Chatelier's principle to the Haber process and see how we can increase the yield of ammonia that then we can use in our fertilizer to produce more or higher crop yields for the people on this planet. So right around the same time as Fritz Haber, there was this gentleman right here, Henry Louis Le Chatelier. And Le Chatelier is a French chemist that lives between 1850 and 1936. And Le Chatelier's principle basically states this. It says that when any system at equilibrium is subjected to change in concentration, temperature, volume, or pressure, then the system readjusts itself to counteract the effect of the applied change and a new equilibrium is established. So let's go ahead and apply this concept to the Haber process. So if we take a look right here, according to Le Chatelier, changing the concentration of a chemical will shift the equilibrium to the side that would reduce that change in concentration. So if we have this chemical reaction right here and we want to increase the production of NH3 here, according to Le Chatelier's principle, if we add more N2, if we add more nitrogen, say from the atmosphere, then the reaction is going to shift to the right and produce more ammonia in order to regain equilibrium. So one way that we can increase the production of NH3 is by adding more N2. And since it comes from the atmosphere, that shouldn't be an issue. There's plenty of this stuff right here. Let's take a look right here. It says increasing the temperature of a system is like adding heat. Heat can be considered as either a reactant or a product depending on whether the reaction is exothermic or endothermic. And increasing the temperature will shift the equilibrium to the opposite side of where the heat is in the chemical reaction equation. So here's our Haber process right here. And we know that the enthalpy of our reaction here is negative 92 kilojoules per mole. And so this means that our Haber process here, or this chemical reaction, is exothermic. And so heat is going to appear on the product side of our chemical reaction. And so according to Le Chatelier, if we add heat to this system right here, if we add heat, it's going to be like adding more product, and the reaction is going to shift to the left. It's going to shift to the left, right? And so more H2 and more N2 are going to be produced in order to achieve equilibrium. And so this doesn't work well for us, right? If we're trying to increase the production of NH3, adding heat here would cause this to shift to the left and more nitrogen gas and hydrogen gas would be produced. However, we must also remember from last unit when we talked about kinetics that if we add heat to a system, it's going to increase our rate law constant for that chemical reaction. So it's actually going to speed up the rate. So scientists, what they do is they can actually increase the heat, taking in the idea that this will shift it to the left, but it speeds up the reaction. And so we ultimately end up having more production of NH3 here. But understand that concept that if we add heat to a system, it's going to shift in the direction away from that heat, in this case to the left. It says right here that if the volume of the container of the system is in is decreased, then the pressure of the system increases and the reaction will shift away from the side that contains the most moles of gas to the side that has the fewest moles of gas in order to regain equilibrium. So here we go. We have the Haber process again, and if we take a close look, we can see that there's 2 moles of gas on the product side, and we have 3 moles here and 1 mole here, for a total of 4 moles of gas on the reactant side. And so according to Le Chatelier's principle here, if we increase the pressure of the system right here, right, if we increase the pressure of these gases right here, then what's going to end up happening is that the reaction is going to shift in the direction of the fewest moles of gases in order to achieve equilibrium. So because we have 4 moles here of gas and 2 moles here of gas, if we increase the pressure of this, it's going to shift to the right. It's going to shift to the right in order to achieve and regain equilibrium. So in other words, because this has 4 moles of gas here and 2 moles of gas here, if we increase the pressure, the reaction is going to shift in the direction of the fewest moles, which is 2 moles, to achieve equilibrium. And because it's shifting to the right, that means that more NH3 is going to be produced. So what are some ways that we can increase the amount of NH3 that is produced in our Haber process here? Well, if we take a look, we can add more N2, no problem. We have all kinds of N2 in the atmosphere. What else can we do? We can add heat. Yes, that's going to shift the equilibrium to the left. However, it's also going to increase our rate law constant and thus allow us to produce more NH3. Lastly, if we take a look here, we can increase the pressure, right? We can increase the pressure and more ammonia will be produced as the reaction shifts to the right to regain equilibrium. So let's take a look at a few more variables that will have an effect on equilibrium and equilibrium shifts. And so let's take a look at more variables that we can manipulate and see what effect it's going to have on an equilibrium. And so if we take a look here, what if we add a noble gas? Let's suppose we have the Haber process here, and what we're going to do with this Haber process is we're going to add helium to this chemical reaction or chemical equilibrium. It says right here that when a noble gas, that is to say gases from group 18, is added to a system at equilibrium, the reaction experiences no shift and will stay in equilibrium because the partial pressures of the gases involved in the chemical reaction remain unaffected. And since noble gases are inert, they are not involved in the reaction process. So essentially, you might think that if we add helium to this chemical reaction right here, that's going to affect the total pressure of this system right here, but that's not the case. It does affect the total pressure, but it does not affect the partial pressures of these gases right here. The partial pressures of these gases are going to end up remaining the same. Therefore, the chemical reaction here is going to remain in equilibrium and no shift will take place. Furthermore, since helium is an inert gas, it's not going to react. It's unreactive with other elements typically, and therefore it's not going to react with either of these two substances that we see right here or this substance right here. So adding helium will not shift the equilibrium in any direction. The system will remain in equilibrium. What about if we add a catalyst? In an earlier video we talked about a catalyst. We said that a catalyst speeds up the rate of a reaction without being consumed in the chemical reaction. And so it says right here that a catalyst has no effect on the position and composition of an equilibrium, and no shift will take place as the reaction will stay in equilibrium. So a catalyst simply speeds up both the forward and backward reactions equally at the same time without being consumed and without disrupting or disturbing the equilibrium. So if we take a look at the Haber process again, we can actually use a catalyst. We can use iron, for example, as a catalyst like we see right here. And this iron is going to cause no shift or no disturbance in the equilibrium. And therefore, no shift is going to take place. The reaction is going to stay in equilibrium. So understand that concept that when we introduce a catalyst, you're not disrupting the equilibrium. And so there's not going to be any shift in the equilibrium. All right, so now let's apply these concepts, these changes in different variables, to some example chemical reactions or some example chemical equilibriums and see whether the reactions are going to shift to the right, to the left, or remain in equilibrium and no shift taking place. In this example right here, it says if the variables below are changed as they relate to the chemical reaction below, then predict whether the reaction will shift to the left, to the right, or if no shift will be necessary to regain equilibrium. So we have a chemical reaction right here that is in equilibrium. We have hydrogen gas reacting with iodine gas to produce HI gas. Furthermore, we can see here that the enthalpy of our reaction is negative 9.48 kilojoules per mole. So what this means is that this chemical reaction here is exothermic. That heat is one of the products. Okay? And so what we need to do is predict which way the reaction will shift to regain equilibrium if we start changing some of the variables that we see right here. So if we take a look here, the first one says H2 is removed. Well, according to Le Chatelier's principle, if we add H2 to this system here, it's going to shift to the right. So therefore, if we remove H2 from our chemical reaction here, the reaction is going to shift to the left to regain equilibrium. Let's take a look at this one. If the pressure is decreased, well, according to Le Chatelier's principle, if the pressure is increased, then the reaction is going to shift in the direction where there are more moles of gas. But we have 2 moles of gas here, we have 1 mole of gas here, and we have 1 mole of gas here. So there's 2 moles of gas on both sides. So if we increase the pressure, because we have the same number of moles of gas on both sides, there will be no shift at all that takes place. This system is not going to have to shift left or right to regain equilibrium because we have the same number of moles of gas on both sides of this equilibrium. What if we add HI? If we add HI, right, if we increase the concentration of HI gas, then the reaction is going to shift away, right? It's going to shift to the left in order to regain equilibrium. What about if we add heat? Well, if we take a look here, this chemical reaction is exothermic. So heat, right, plus heat, heat can be considered one of the products of this chemical reaction right here. And so if we add heat to this, if we add more of this product here, that's going to be similar to us adding HI in the example previous. If we add heat to this system right here, this system is going to shift to the left to regain equilibrium. So by adding more heat or by adding more product to this chemical equilibrium, the reaction here is going to shift to the left to regain equilibrium. What about this last one here? If we decrease the volume of our container, well, if we decrease the volume according to Boyle's law, right? If we decrease the volume, then the pressure of these gases is going to increase. And according to Le Chatelier's principle, the reaction is going to shift in the direction where there are more moles of gas. But once again, we have 2 moles of gas here, and we have 2 moles of gas here. We have 1 mole of gas here and 1 mole of gas here. So on the reactant side, we have 2 moles of gas. On the product side, we have 2 moles of gas. So if the volume is decreased, thereby increasing the pressure, there should be no shift in this equilibrium. All right, so that is how we can apply some of Le Chatelier's concepts to this example right here. Let's take a look at a second example. In this second example, it says, if the variables below are changed as they relate to the chemical reaction below, then predict whether the reaction will shift to the left, to the right, or if no shift will be necessary to regain equilibrium. So we have a chemical reaction right here. It looks like N2O4 gas is in equilibrium with NO2 gas. Furthermore, what we know is that this is going to be an endothermic process, right? We know the enthalpy of our reaction here is 57.2 kilojoules per mole. And because this sign is positive, that means that this chemical reaction here is endothermic, meaning that it's going to have to absorb heat, right? Or it absorbs heat. And so what we have to do here is figure out whether this chemical reaction or equilibrium here is going to have to shift to the left or to the right, or if no shift at all will be necessary to regain equilibrium if we start changing some of the variables here. So this first one says, what if we add N2O4? If we add N2O4, if we add more reactant, according to Le Chatelier's principle, the chemical equilibrium will shift away or to the opposite side so as to achieve equilibrium. So if we're adding more reactant here, this chemical equilibrium will need to shift to the right in order to regain equilibrium. What if we remove NO2? Well, let's think about this. If we add NO2, if we add more product here, the system here is going to shift to the left to regain equilibrium. But because we are removing NO2, the system is going to have to shift to the right to regain equilibrium. What if we heat up the container? This is a good one here. If we take a look here, we see that this is endothermic, meaning that the reaction must absorb heat. It's going to absorb heat. And so because it's endothermic, heat is going to appear on the reactant side. And so what if we add more heat, right? We want to heat up the container. So if we add more heat, or if we add more reactant here, just like we did in the first example here, if we add some of this, it's going to shift to the right. If we add more heat to this system, well, the equilibrium will have to shift to the right in order to regain equilibrium. So by adding more heat to this system here, it's like adding more reactant, and the chemical reaction is going to need to shift to the right again to regain equilibrium. What if we decrease the volume? Well, if we decrease the volume of the container that this is all taking place in, we can see we have two gases here, then the pressure is going to increase. And according to Chatellier's principle, if the pressure increases, well, we have to take a look at the total number of moles on both sides of this equilibrium. We have 2 moles of gas here. We only have 1 mole of gas here. So if you increase the pressure by decreasing the volume of the container that these gases are in, then the chemical reaction is going to want to shift in the direction of fewest moles of gas. So we only have 1 mole here. We have 2 moles here. So the chemical reaction here will have to shift to the left in order to regain equilibrium. Let's take a look at this last one. It says, what if we add helium? Well, we know helium is an inert gas, and so it's not going to react with any one of these reactants or products, right? It's not going to react. But you might be thinking, well, if you add more helium, then the pressure of this system increases. Yes, that might be true. However, the partial pressures of N2O4 gas and NO2 gas remain unchanged. The partial pressure of this gas and the partial pressure of this gas remain unchanged, even though the pressure of the entire system is increasing. So if we add an inert gas like helium to this system here, it's really not going to have an effect on the partial pressures of these two substances involved in this chemical reaction right here, and therefore no shift will be necessary to regain equilibrium, because it's not going to have an effect on this equilibrium at all. So understand how Chatellier's principles work, or Chatellier's principle works, and understand how to apply it to different chemical reactions when we start changing the variables that we see right here. If you like what you see, go ahead and click that little bomb in the bottom right hand corner, and that will subscribe you to my channel. And feel free to leave any comments or questions in the comment section down below, and I really hope you guys found this helpful.